3.2b, logarithmic fun. All right, so we need to talk about the properties of logarithms. All right. Again, how do you solve a log? Log base a of b is equal to c, so it's solved by what? A to the c is equal to b. All right, so if I have log base a of 1 is equal to 0, well, just like Lamont did, you do a to the power of 0 is equal to 1. All right, and so anything, when I have a of 1, it's going to be 0 because anything to the 0 power is 1. All right, and then if we have this right here, if I have log base a of a, that's equal to 1. All right, that's kind of called an identity almost. So that's what happens there. And then if I have log base a of a to the x, that's equal to x. This is really what happens. This x actually comes out front. All right, that x actually comes out front. So then you end up having x log base a of a. And what did you just learn about log base a of a? That's 1. So it's really x times 1. That's really what's happening. It comes out front. All right. It's called the power property of logarithms. All right. And then if you have log base a of x is equal to log base a of y, this is again using the one-to-one property. So then you have log base a of the same. So it's just x is equal to y. All right. So let's put it into practice. All right. So part A, I have log base 4 of 1. So if I have the equal to c or something like that, how do you solve a log? So we'd have 4 to the power of c is equal to 1. And so c would equal what here? C would equal 0. Or you could just memorize this like property of logarithm, and you could go from there. All right? So the next one, we have log base square root 7 of square root 7. So my base and my of are the same thing. That's equal to what? 1. All right. And then let's do this one. So now I have a log. No, just kidding. I have 6 to the power of log base 6 of 20. All right. And so on this one, I need to remember my inverse property. And so that would equal that would actually be 20. All right. It's set up just like this inverse property. Okay. So now we're going to use the one-to-one property a little bit more, but we need to have them have the same bases, and then we can go from there. All right, so I have log base 3 of x is equal to log base 3 of 12. Well, do they have the same base of these logs? Yes, so I can use what's called the one-to-one property, just like the exponentials. So then I get x is equal to 12. That's it. That's all you're doing. This next one I have log base what? What is my base there? It doesn't have one. It's 10. Okay, remember if it's not explicitly shown, it is log base 10. So I have the same bases on these, so then I end up with 2x plus 1 is equal to 3x. And then I need to start solving for x. So what do? I subtract 2x. So then I get x is equal to 1. I get x is equal to 1. All right, this next one. I have log base 4 of x squared minus 6 is equal to log base 4 of 10. Well, they have the same base, so again, I can use the one-to-one property. So now I'm left with x squared minus 6 is equal to 10. How would I start solving this guy? I add 6, so then I get x squared is equal to 16. And then what? I square root it, so I get x is equal to 4. Plus or minus 4. Very good. Whenever you square root, what do you have to do? A plus or minus. So I don't like it written like that. I say x is equal to negative 4 and x is equal to 4, just to make sure that you know that it's two solutions. Okay? Good? All right. Now we're going to talk about graphs of exponentials and graphs of logs. All right, we've actually talked about both, but now we're going to kind of piece things together and show the relationships between them. All right, so if I were to change f of x, I could change that to y. Okay, I'm kind of going backwards on Euler's notation. So if I have y is equal to 2 to the power of x, do you remember where these things cross? Not just 1, but 0, 1. Remember? Remember they're going to cross the y-axis at 1. Okay, so it's going to cross at 0, 1. Remember? Remember that? All right, and they actually have a horizontal asymptote at what? Y equals 0. Okay, so we already know that exponential. True that? Remember graphing those? Now let's talk about this log. So if I have log base 2 of x, let's substitute in some points. All right, let's do I don't know. Let's do log base 2 of 1. Why not? All right, and if I say it's equal to c, well, then I'd actually have 2 to the power of c is equal to 1. Well, what does c equal? 0, right? So c would equal 0. So log base 2 of 1 is actually 0. So I would actually have the ordered pair of 1, comma 0. All right. And so I'd have it kind of right there. All right. And then let's say we did log base 2 of, let's say 4. Let's say 4. All right. And so how would we solve that? I would say 2 to the power of c is equal to 4. And so what would I end up getting for c? C would equal 2. So that ordered pair would be what? 4, comma 2. That'd be 4, comma 2. And so I'd have this point up there. Now, what if we did something like log base 2 of, let's say, 1/4? And I set it equal to this thing called c. So I solve a log by doing 2 to the c is equal to 1/4. Well, this is my childhood. What does c have to be here? It's a negative 2. All right? So then I end up with a negative 2 going on there. So I end up having 1/4, comma negative 2. And so I actually have this as my log. All right? I actually have that going on as my log. Now, what's the difference between this exponential and this log? We did it in chapter 1, section 9. What happened? They did what? They reflected over y equals x. But I want you to give me that term. What really happened? If I switch x and y, they're inverses of each other. Exactly. So exponentials and logarithmics are inverses of one another, which really means what? They are a what? A switch in x and y. Because look at it, guys. If I have 2 to the power of x, if I substitute in 2, what am I going to get? If I substitute in 2 for x, what do I get for y? I get 4, right? True? You agree with me? All right. And so if I actually substitute in 4, well, what do I get for my log? I get 2. What happened? It's a switch in x and y. You following me? All right. So that's really what's going on. So my exponentials are usually going to cross where? At 0, 1. At 0, 1. Now, where are my logarithmics going to cross normally? At 1, 0. All right? Because it's a switch in x and y. All right? So if you look at it, if I do this log, I have y is equal to log base 2 of x. How do you solve a log? A to the c is equal to b, right? So this would end up being 2 to the power of what? What's my c here? My y. It'd be 2 to the power of y, which is equal to what? X. What's the difference between this and this? What happened? It's a switch in x and y. All right? That's not on mistake. That's not on accident. Okay? That's how they work. Okay? All right. So let's talk about transformations of logs. Where do logs usually cross? At 1, 0. Okay? And they're a slow-moving function. They go up. All right? So they usually cross there. Now, if I look at this one, I have log base what? This one's what? What's this base? 10 of x minus 1. Well, what happened? This is x minus 1. Is it inside or outside? It's inside. So what does it do when it's inside?
Goes to the right.
It moves right or left. In this case, it moves right. Okay, it moves right how much? 1. So instead of crossing at 1 comma 0, now it's going to cross at 2 comma 0. All right, this next one I have is 2 plus log of x. Is this inside or outside my function? It's outside. It's outside my function. So what's it going to do? It's going to move up 2. So instead of crossing at 1 comma 0, where's it going to cross? At 1 comma 2. Okay? All right, let's keep moving. All right, this is what's called a natural log. Okay? So if we have natural log of x, that's what's called a natural log. And natural log x is actually a log base e. Remember I said e is your natural base yesterday? E is 2.718281828, and then it doesn't repeat after that. So if you have log base e, that's the same thing as saying natural log. All right? I don't like it being called natural log because I'm like, natural log should be an N and an L. This is a what? An L and an N. I think it should be called log au naturel. All right? But then I think it's like a shampoo, you know what I'm saying? All right? So anyway, that's natural log. Okay, however, this natural log, who's it's inversed with? A natural log is actually inversed with what? E to the x. All right, which is really a switch in x and y. All right, so they actually have a buddy system going on. So I'm going to do natural log of 2. Let's make sure we know how to do this. So natural log of 2, which is equal to 0.6931. All right. I want to kind of go over what natural log of 2 really is. Natural log of 2 is really a log base e of 2. And if I were to try to solve that with old school methods, that's really e to the power of c is equal to 2. However, can you do e to the power of something gives you 2 in your head? Probably not, unless I wouldn't have you in this class if you could. All right, so that's why we have this little natural log button. All right, that's really what's happening though. All right, this next one, I have natural log of 0.3. So what do I get? Negative what? Is it 3.9? It's 4.0, right? All right. Why is it negative? Because it's less than 1. It's in between 0 and 1. That's why it's negative. Because where's the natural log going to cross? At 1 comma 0. So anything greater than 1 is going to be positive, and anything between 0 and 1 is going to be what? Negative. All right, so that should be kind of your check on it. All right, now I'm going to do natural log of negative 1. Jasmine, what happened? Doesn't exist. Why doesn't it exist? Because it's negative. Okay, again, your logarithms, just like yesterday, it can't actually accept a negative response because you can't say e to the power of something gives you a negative 1. All right, that's really how it's working. All right, this next one. I have natural log of 1 plus square root 2. All right, obviously everybody's going to do that one in their head. Emily, what did we win? Good. All right. Pretty good in their head? All right. So again, just like properties of logs, there's properties of natural logs. They're the same thing, actually. Just like the regular logs, they still work the same. All right, instead it's just log base e. All right, so let's look at part A. I have natural log of 1 over e. Well, this is kind of different. Why did my e go on the bottom? Because he's a negative what? Exponent. So this is really natural log of e to the negative first power. That's really what's happening. All right, that's my childhood. All right. So really, this is what the power property is doing. This -1 actually comes out there. And so this is really -1 times natural log of E. Well, what is natural log of E? The bases and the of are the same. So what's natural log of E? 1. All right, so I have -1 times 1, which we call -1. All right, let's look at part B. I have E raised to the power of natural log 5. So what is it? I have E to the natural log, or log base E of 5. They kind of cancel, so what do I get? I get 5. This is number 3. All right. Part C. I have natural log of 1 over 3. Well, what is natural log of 1? What's log of 1? 0, right? So now I end up having 0 over 3, which we're still going to call what? 0. All right, this next one I have 2 times natural log of E. Well, what's natural log of E? 1. So it's really 2 times 1, and we're going to call that 2. A freestyle. What if I have natural log of E squared? What if I have natural log of E squared? What happens? What happens? What happens to my 2? It gets to do what? It gets to be brought out. All right? So this is really 2 natural log E. All right? And what is natural log E again? It's 1. So this is really just 2 times 1, which is 2. So natural log of E squared is actually the same thing as saying 2 natural log E. All right? That is the same thing. So now we're going to find domain of each one of these logs. All right? And I'm actually going to do one more from your homework before we leave. All right? So this natural log of x minus 2. All right? So what can we have as our inputs for our natural log? What can we not have? Let's go that route. We can't have a negative. All right? We can't have a negative in my domain for my logs. Remember? Because when you type in natural log of -2, what happened? There's a domain error. And really, it's because my a to the c equals b thing going on. All right? So what we have to do is we need to set what's inside greater than 0. So I say x minus 2 is greater than 0. Which means what? X is greater than what? X is greater than 2. Which means my domain is what? Where does it start? My domain, it starts at 2, and then it goes to infinity. All right? X is greater than 2 is the same thing as saying 2 to infinity. All right? Now, what really did it do? It shifted which way? It shifted right 2. So instead of crossing at 1, 0, now it's going to cross at what? 2. At 3, 0. All right? So that's what it's doing right there. Okay? All right, let's look at this next one. I have natural log of 2 minus x. I have natural log of 2 minus x. So I need to set this thing greater than 0. So I say 2 minus x is greater than 0. So what do I get now? I get x is less than 2. I get x is less than 2. So what's my least value I can have? Negative infinity. I get negative infinity. And what's the biggest value I can have? I can have 2. Now, so now my domain is negative infinity to 2. All right. So let's just talk about this real quick. All right. This x changed to negative x. So it changed its x. So what did it flip over? Changed its x, so it flipped over the y-axis. All right. So that's why instead of our natural log going like that, guess what it's doing? It's going that way. Okay? And so it flipped over the y-axis. That's what just happened to it. I'm not actually worried about part C. Okay? That's a wombat. A wombat. Wombat. Do you know who the guy is? All right, somebody read the directions for 39. Go ahead.
Exercise 3744, find the domain x-intercept and vertical asymptote of the logarithmic function in sketches graph.
Domain x-intercept and what?
Vertical asymptote and sketches graph.
All right. All right. So let's do domain. Let's do domain. So we just need to set the inside part greater than 0. So my inside part is just what? It's just x. All right? It's just x. All right? If I had a parenthesis, it'd be x plus 2. All right? But I don't have a parenthesis, so it's just x. All right? So my domain, I just say x is greater than 0. Now, how do I write that in interval notation? That's the way we're going to be tested. How do I write that in interval notation? 0 to infinity. All right. All right, now let's do x-intercept. Let's just go in order. Well, actually, let's do vertical asymptote because it goes along with it. Our vertical asymptote is when we set this inside function not equal to 0. All right. And so really, where's my problem area going to occur? At what? At 0. So my vertical asymptote, I basically set my inside not equal to 0, so I can't get 0. So my vertical asymptote is x is equal to 0. All right. So that's really all we're looking for. Now let's do x-intercept. How do I solve for an x-intercept? I set the y equal to 0. So now I say 0 is equal to negative log base 3 of x plus 2. So now I need to start solving for x. Well, it's the opposite of order operation. It's SADMIT. So what do I need to do first? I subtract 2. So when I subtract 2, I end up getting negative 2 is equal to a negative log base 3 of x. Well, now what? Choom choom. All right, because we got a negative log, I got to distribute the negative or divide by a negative 1. And now, how do we solve a log? Bless you. A to the c is equal to b. So what's my a? 3. What's my c? Is equal to x. So x is equal to 9. Can I keep that as my answer? No, because that's a line. So what's my x-intercept? 9, 0. All right. And then we're ready to sketch its graph now. All right. So I have an x-intercept at 9, 0. There's my 9. And then I have a vertical asymptote at x equals 0. All right. Now, we got to figure out what this thing does. What did this negative thing do? That flipped it over what? It changed its y, so it flipped it over the x. All right. So a normal logarithm goes this way. Remember? So if we flip it over the x, which way does it go? It goes this way. All right. So now we're going to be going that way. Now, yes, it's going through 9, 0. However, this 2 made it do what? Made it go up 2. So really, what's it actually going through? 1, 2. That's really what it's going through as well. All right, now, I'm not going to require that. However, that's the way I actually want you to think about it. Okay? All right, and wouldn't that make sense that it's going downward now? It's got to go through these two, so obviously it has to go downward. Yes, ma'am.